So far in the chapter, we did learn about how is sound produced, okay, how it travels from one place to another, okay. Can sound travel in vacuum?
No, sir.
Uh-huh. Obviously, no. Okay. We also discussed that each object has a distinct sound, right? Each object produces a distinct kind of sound. Okay. No? So we learned that sound is a form of energy, right? It's that form of energy which makes us hear, right? Then each sound is special to the object which produces it. We learned about that. It is always produced due to vibration of the objects. What happens when an object vibrates? So, when an object vibrates, what it does, it it sets motion in the particles near it. The particles of the medium start to vibrate, and they carry the energy with them, right? And they carry the energy with them. Okay. So we learned about that also. Further, we learned that in the case of we humans, the sound is produced by the larynx or basically the voice box. Okay. Further, we discussed that sound travels in the form of waves. So we learned that waves are basically kind of disturbances that travels through the medium. Right now, they basically carry the energy with them without the transport of the object that is producing that energy. For example, in this case, the sound is traveling in the form of the waves. Okay, so the energy is being carried with this wave, not the source of origin of that sound. The energy is being carried. The sound travels in the form of waves. Okay, and we learned one more thing, that sound is an example of a mechanical wave which requires a medium, while light is an electromagnetic wave which does not require a medium for its propagation. I also told you that how you can understand this, how you can visualize this, right now. So when sound is produced near a moving water, so those vibrations, right now, those vibrations sets movement in the water also, right now, as sound is traveling in the form of wave. So this video clearly tells us how it travels in the form of the waves. Okay. So we learned about that also. We learned about how the density of the medium also affects the speed. If the density of the medium increases, so the speed of the sound also increases. As you know, solids are denser than liquids and gases. So thereby the speed of sound is maximum in solids, right? It is maximum in solids, and it will minimum in liquids. Sorry, in gases. It will be minimum in gases. We had learned about that. Okay. In fact, you guys can do some activity also in order to understand how sound travels. Like what you can do, you can take two empty tin cans. Okay, you guys might have got this project, or maybe you guys can get this project also from your school. Like you can take two empty cans like that, connect these two empty cans with the piece of a thread. Say that you have taken a 15-meter long thread. Okay, it should be a thick thread, by the way, not a very thin one. And you have taken tin cans. Okay, you have taken tin cans. Okay, and both of them should have a small hole. Both of them should have a small hole at the center of its bottom. Okay, and both of them should have a small hole at the center of its bottom to which you will be connecting it. Like basically, you will make a small hole and somehow you will connect it to thread. Okay, so you will observe that if one of the children were to speak, suppose if one of you were to speak on this. Okay, so the sound can be heard by the child at the other end also. Like if another child here is putting his ear on it, okay, so he can actually hear it. He or she can hear the sound, right now. So in this
Yes, sir.
case, like you have basically made a toy telephone. Actually, we can call this as a toy telephone, right now.
Hello, sir.
Yeah, yeah, I'm listening. Who was that? Okay, see. So that is a toy telephone. Further, we discussed about the construction of this of the human ear also. Right now, how the sound travels through the human ear, how does the different parts works together. Okay, so our the human ear can be divided into three different parts. One is the outer ear, then middle ear, and then the inner ear. We learned that the sound waves travels in the outer ear, that it first, like, it is collected by the earlobe and the ear pinna, then the sound wave travels inside the ear canal. Okay, also called as auditory canal. Then those sound vibrations, they hit the eardrum, and the eardrum passes on the vibration to these ossicles, to the three tiny bones present in your ear. That is basically malleus, incus, and stapes. They all also start to vibrate, and they amplify the vibration further. And those vibrations are now further sent into the inner ear, into the inner ear. Now, in the inner ear, basically we have this coiled tube-like structure that is called as cochlea. Now, this cochlea is filled with some liquids, and that has cells, that has nerve cells which are very sensitive to the sound. So, when the liquid starts to vibrate, when the liquid present inside the cochlea starts to vibrate, so thereby the nerve cells, they get stimulated, they get triggered, and they start producing electrical signals. They start producing electrical signals which are then carried by the auditory nerve. This right here is the auditory nerve, and the auditory nerve carries the electrical signal to your brain, and then your brain interprets that, and that's how the human ear works. Okay, so we did learn about that. So far some basic things we have discussed, like sound is produced by vibration of the objects, and they travel from one place to another in the form of waves. Okay, now how does this wave move? So let us understand about that also. Okay, so to understand how sound works, like how it moves, how does the sound wave moves, imagine you have dropped some stone, you have dropped some pebbles into a pond. So when the pebble hits the water, it will create ripples like that, right, everyone? All of you turn your cameras on. Abu Bakr, Priyanka, and Mustafa, you still haven't connected with to the audio. Hmm. So ripples are created, and these ripples start to spread in all the direction. Similarly, when something makes a sound, like you're clapping your hand or you're speaking or you're ringing a bell or something, so it causes vibrations similar to these ripples in the water. It creates vibration, and those vibrations spread out in the form of waves. Now the question is, how does these waves travel? To visualize it, look at this. To look at this. Oh, no, no, look at this one particularly. So here what you will see, that when the particles of the medium, like when the particles of the medium, they will start to vibrate. Okay, they will start vibrating. And how are they vibrating? They are vibrating kind of parallel to the direction in which the sound is moving. Like as I'm speaking, so sound is traveling in this direction. This is the direction of sound. Okay, and remember, earlier I have shown you this animation where you were seeing that the particles were actually traveling in the form of compression and rarefactions. Particles were coming closer and moving farther, closer and moving farther, just like how a slingy moves. Just like how a slingy moves, like this. This is a slingy, just like how this is moving. So the particles of the medium are also moving further, while the direction of, like, it is moving kind of parallel to the direction in which the sound is moving. Getting it? So we say that sound travels as longitudinal waves. When the particles of the medium, they travel parallel to the direction of the wave motion. So in the means of successive compression and rarefactions. So this is the way how sound travels. This is the way how sound travels, as we can see here. The particles, they are coming closer and they are moving further, closer and moving further. So in the form of compression and rarefaction or expansion, the sound is traveling. So this way in which sound travels, that is called as longitudinal wave. So sound travels in the form of longitudinal waves. Is that clear to everyone what I'm trying to say? These particles are vibrating. They're coming closer, moving further, closer, moving further, just like how this slingy is moving. So you can imagine like the particles are actually coming closer and moving further, closer and moving further. As I'm speaking right now, so what is happening? All the particles in front of me, the air particles, they are coming closer and moving farther away, closer and farther away. So in the form of compressions, where the particles become very close to one another, and in the form of expansion or expansion is same as the rarefaction here, where the particles move away from one another. So in this manner, the sound wave travels. Okay, in this manner, sound wave travels. Okay. Well, there is one more type of wave which you already, by the way, don't have to learn about, but that is a transverse wave. An example of that is light, where the particles of the light, okay, na, they are moving perpendicular to the direction in which the light is moving. Understanding it? Just like, for example, you take this Mexican wave, for example. Okay, how the fans are cheering like that. Okay, so say that this wave is moving in this direction and they are jumping up and down like that, kind of. So answer the following question: which of the following is an example of a longitudinal wave?
Sound waves.
That is clearly sound waves. Okay. In the case of transverse waves, the particles of the medium move. This is the direction in which the wave is moving, while the particles they move up and down like that. No, getting it? Like they are moving perpendicular. So they move perpendicular to the direction of the wave. Okay. Third question: sound waves cannot travel through.
Vacuum.
Obviously, that is vacuum. Okay. Now we are going to learn about some important terms that are associated with sound. Okay, no? So that is amplitude, time period, frequency, few more terms which we are going to learn about. Okay. Now, before we continue with this, like how can we prove that sound does not travel in vacuum? So for that purpose, what we can do a simple activity. Suppose you will take a glass jar, you will take two different glass jars like that. In this, air is present, and this one air is present, and here you have placed a alarm. We have placed a alarm bell, suppose. So that is the switch. Okay. So when the switch will be turned on, the alarm will start to ring. And can you hear the sound of it?
Yes, sir.
You can obviously hear the sound right now. You can hear it. Okay. The sound is heard in this case. But in the another case where you're having vacuum, and if an alarm is being turned on, okay, if the switch is turned on, even though the alarm will ring, it will ring, but you won't be hearing the sound right now because the thing is that there's a vacuum, there's no medium in it. So the glass jar that is containing the bell, okay, no, containing the bells in it. If in one of them using a vacuum pump, we have to remove all the air. So when we switch on it, when we turn on the switch of the electric bell, we cannot hear the sound because we know that sound cannot travel through vacuum. Okay, hope that is clear. Sorry. Talking about the different terms associated with the sound, let us understand that. First, we are going to learn about the wavelength. Like, what does wavelength mean here? See, you look at the falling wave here. Okay, this is a wave. We are saying it's a sound wave. So it looks like cliffs. It kind of looks like cliffs right now. Kind of looks like cliff. So the top of the cliff, we call this as crest. right? We call this as crest. And this one here is called as trough, trougf, trough. And that is again crest. And if you were to continue it further, this will be another trough, right? So the distance between two crests is called as wavelength. The distance between two crests of a wave is called as wavelength. Understanding that, everyone, what I'm trying to say.
Yes, sir.
Priyanka, what
Yes, sir.
about you, Abubakar? Getting it? Okay.
Yes.
So wavelength is basically the distance between two successive crest, or we can say between two successive trough also. Like that also we can define it. Okay. Now the question is that why are we learning about it? Like what is the use of the wavelength? Huh? So for that purpose, first we learn about frequency, then we're going to get back to wavelength once again. Okay. Talking about frequency, so frequency basically refers to number of vibrations, okay, or number of waves that is produced in 1 second. It basically refers to one second. I have to clean something. Hmm. Talking about the frequency, I was saying that frequency basically refers to the number of waves or number of vibrations completed by an a number of waves or vibrations produced in 1 second. That is called as frequency of the sound wave. Okay, that is called as frequency of the sound wave. Okay. Now let's get back to this image here. See, there are two different sound waves here. There are two different sound waves. We can clearly see that the frequency of this one is actually more than the frequency of the second one. Because suppose that we have taken a time period of 1 second here, and this is again 1 second. So in a given period of 1 second, you can clearly see that more number of waves have been produced here. There are lots of waves in this one, but this one has fewer waves. Right? Getting it, everyone?
Yes, sir.
Okay. So what does it mean that if the frequency is more, so wavelength is less? You can see here. Or we can say the other way also, that shorter wavelength means there are lots of waves. Shorter wavelength means lots of waves are going to be there. Understanding how wavelength and frequency is related here once again. If the length of the
Yes, sir.
wavelength is lesser, it means there are more number of waves. But here, the wavelength is longer, it means there are fewer waves. So fewer waves means low frequency. While shorter wavelengths means high frequency. Try to relate it, it's actually important in the string. Okay, now? And how do we calculate frequency? So frequency is equal to number of oscillation divided by total time, or simply we can call it as number of vibrations divided by total time. Total time. And frequency is just opposite of time period. Here, T stands for time period. We are about to learn about time period also in a while. Okay, so don't worry about this relation between frequency and time period. Then the unit of frequency is expressed in hertz. It is hertz, in short, written as capital H in a small set. Suppose if a frequency of 20 hertz is written, so it means that the object is vibrating 20 times. There is 20 vibrations in 1 second. In under 1 second, there's 20 vibrations. Getting it, guys? Or if an object oscillates or vibrates for 80 times in 1 second, so then its frequency will be equal to 80 hertz. Okay. So if it's like that, so what does 1 hertz mean? Any idea? What will 1 hertz
So
mean?
one vibration in 1 second.
Exactly. So that will mean one vibration in a period of 1 second. Okay. You guys turn your cameras on. Abu Bakr, Priyanka, turn your cameras on. Okay. Now, how does the frequency affect the quality of the sound? How does it affect? We generally get to see that boys have a deeper sound while girls don't have a deeper sound. They have kind of a shrill sound. We call that a shrill sound. Okay. So pitch is the quality of the sound that depends upon frequency actually. Right now, it means suppose that if someone has a low frequency sound, like the frequency of the sound wave is low, it means that they will have a low pitch, right? Boys generally have a low pitch. But if there's more frequency, again you can understand in the following manner. The time here given to you is 1 second. So under 1 second, you can clearly see that more number of waves are produced in the second emission of, right? More waves are there, more vibrations are there. More waves means more vibration. So thereby frequency is higher, and higher frequency means it's higher pitch. Understanding, guys? While lower frequency means low pitch. Okay. Is that clear or is it a bit confusing? Tell me. Abu Bakr, Priyanka,
It is
Sir,
clear.
clear.
clear? Okay, good. So relation between frequency and pitch is like they are having a direct relation. Higher frequency, higher pitch. Lower frequency, lower pitch. Okay, good.
Okay.
You guys answer this question. 1 second, please. First, you guys answer this question. The distance between two consecutive compressions or rarefaction in a sound wave is called.
Wavelength.
Priyanka, what about you? Is the answer correct?
Yes, sir. The answer is correct.
The answer is correct now. Right now. So distance between two consecutive compression or rarefactions in a sound wave, or we can say distance between two consecutive crest or trough in a wavelength, right? Or you look at this image also here. 1 second. See, if I were to talk about the distance between two compressions here, so that is same as wavelength here, right? Okay. So you have to actually keep multiple things in your mind in order to fully grasp it. Okay. So that is wavelength. Next question.
Hertz.
Hertz.
That is clearly hertz. The third one. I will draw the diagram for this one. Okay. Now, suppose there are two sound waves. First one is like that. Okay. And say that this is the wavelength of it. That is the wavelength of this first sound wave. Then you are having another sound wave whose waves are like that. Okay. And say that this is the wavelength. Clearly, the second one is having a shorter wavelength. No?
Sir, decrease.
Mm-hmm.
Sir, B.
Exactly.
So it decreases.
Decreases now. Getting it now. Because frequency, what do we mean by frequency? Frequency means the number of vibrations produced in 1 second now. Right? In the first one, the wavelength is more, right now. The wavelength is lengthier, like it is more. It has increased. So thereby, less number of waves are there. Less number of waves means less frequency. While in this one, the wavelength is shorter, so more number of waves are there, hence frequency is higher. So it is clearly decreases. Okay. Answer some questions related to frequency also. The unit of frequency is
The hertz.
hertz. Priyanka, are you not getting it? Like you're not answering?
I am getting it. Like
Okay.
some the voice
Okay.
is not.
Oh, okay. Okay. Hmm. The frequency of a sound wave is the number of dash that passes through a point in 1 second.
So vibrations.
What about you, Priyanka? Yes.
Sir, vibrations.
Vibrations. Good. Her voice is not reaching like that is vibrations. Okay. Good. Say if a sound wave has a frequency of 2 hertz, how many vibrations does it make in 5 seconds? Okay. So for that purpose, there was this formula that is frequency equals to total number of vibrations upon total time. Okay. So frequency equals to total vibrations divided by total time. In the above question, what is given?
Sir, is it 40?
So 40.
Sir, 40 hertz.
It is 40 hertz
For
indeed. No, 1 second. Frequency is 2 hertz, while total time is no. See, guys, in the question, what is given to you is frequency actually. See, frequency is 200 hertz, okay? Then time is given to you. This and this is actually given. Time is 5 seconds. No? You needed to find the total vibrations that is being produced there. Understanding what the question was asking now.
Yes, sir.
So total vibration is going to be the product of frequency and time. Isn't it, Priyanka?
yes,
Like
sir.
this and this get multiplied. So that is equal to now how much?
Sir, 1000.
1000.
1000 vibrations were actually being produced. Okay. Make sure you guys memorize this formula. Frequency equals the total vibrations or total oscillations divided by total time. Okay. Usually you will find the term vibrations only in the question. Okay. True or false?
Sir, the
Higher
answer is
frequency.
200 hertz.
Oh, which one you are saying? 200 hertz.
So like we found the vibrations, then you have to find the
Frequency was already given, no? Like frequency was already given 200 hertz.
oh
You
yes
had
sir.
to, no issues. You had to find how many vibrations was it making in 5 seconds. Okay.
Yes sir, got it.
Higher frequency sounds have a lower pitch. Is it true?
False.
False. Very good. Because
False.
frequency and pitch has a direct connection. They are directly related. Okay, not directly proportional. One increases, another also increases. Okay, next.
True.
That
Sir,
is true
true.
indeed. Very good. Okay. Also, once more, I will ask you question related to the wavelength. So you guys tell me about it. If the wavelength increases, what happens to the frequency?
It decreases.
That is decreases. Very good. So then, is the opposite also true? Is the opposite also true? Like if the wavelength decreases in size, here you are having shorter wavelength. So does the frequency increases?
Yes, sir.
Exactly, it increases now. You can clearly see there are more number of waves produced here, so means more frequency. Good. Now another term here is time period, and this one more that we'll be learning, that will be amplitude. Okay. Talking about the time period here. See, I will give a simple definition for it. Okay. See, time period is simply the sorry, total time taken to produce the total number of vibrations. Okay, and total time taken to produce the vibrations. Okay, suppose for example, here, let us suppose that, let's assume that 10 vibrations were produced. Suppose, okay, now the picture is just for reference. So 10 vibrations were produced. Okay, and in order to produce these 10 vibrations, okay, the time that it took was, let's say, 5 second. Okay, 5 second. So thereby time period will be equal to total time taken here, that is 5 upon total vibrations. So that is 0.5. Okay, no, that is 0.5. Meaning that the time period, like in order to produce one vibration, it took 0.5 second. Getting it, guys? In order to produce one vibration, it took 0.5 seconds of time. Now suppose if in this case we had to find frequency, so frequency will be just opposite of it. For frequency, it is total vibrations divided by total time taken now. The total vibration is 10 and total time is 5. So 10 upon 5, that is going to be 2 hertz. So 0.5 is just inverse of 2 hertz. Understanding that or not?
Yes, sir.
Because like inverse of 0.5 is what? If you were to invert it, like 0.5 is 5 upon 10. Okay. And inverse of 5 upon 10 is 10 upon 5 now. That is 2. Right? So the time period is inversely related to frequency. It is inversely related to frequency. It basically tells us like how many vibrations are produced in 1 second. How many vibrations are produced in 1 second? A bit confusing, I think, huh? Tell me.
No, sir.
Yes. No?
No,
Okay,
sir.
good. Right now. Just like in the pendulum, you guys have learned no? In the pendulum bob, one complete to and fro movement of the pendulum bob is called one vibration or one oscillation, and then the time taken by the pendulum bob to complete one vibration or one oscillation, that is called as the time period of the pendulum. Okay, you'd be able to recall that when the pendulum bob moves from one position to another, and like when it moves from, suppose, let me tell you that once again. This is the pendulum bob, position A, position number B, and position number C. Right. What we have learned that when it does a movement where it goes from position B to C, right? Position from B to C it goes and back to B. So that is called as, what do we call that?
The one oscillation.
One oscillation, exactly. Okay. So about the time period I'm saying, the time taken, if we were to talk about the time period of the pendulum. So there it means the time taken by the pendulum bob to complete one oscillation is called the time period of that pendulum, right? Similarly, the time taken by a vibrating object to complete one vibration will be called its time period. Getting it now? So one vibration means one wave, you can say, right now. One vibration you call it as one wave like that. Hmm? So the time that will be taken by a vibrating object to complete one vibration, or let's say one wave, that will be its time period. Okay. Or in other words, it's simply the time taken by an oscillating object to complete one oscillation. So that is its time period. And how do we measure it? So it is measured in second. The formula is time taken by total number of oscillation or vibrations produced. Okay. Also, by now it should be clear that frequency and time period are having an inverse relation. If suppose a question was given that where the frequency is given and you had to find the time period, suppose just a question where frequency is given, let's say 20 hertz, and you are supposed to find what is the time period. So you know the relation between them, that frequency is equal to 1 upon time period, right? Okay. So you are going to put the value 20 equals to 1 upon time period. So time period equals to 1 upon 20, isn't it? So 1 upon 20 is how much? 0.05, right? Yes or no?
Yes,
0.05
sir.
second will be the answer. Okay. So relationship we have discussed here. Let's learn about the amplitude. In the simplest word, amplitude is simply the height of the wave. It shows us how strong or intense the sound is. If the height is more, so thereby the sound is going to be louder. Right now, if the amplitude is larger, if it is higher, then it means that the sound is louder. But if this amplitude, the height of the sound wave is smaller, it is low, so it means that the sound is softer. Right now, you can think it of the following manner, like when you turn up the volume of some audio device. So when you're turning on the volume, so you're kind of amplifying it, right now. There's a key called as amplifier also. Amplifier button is there, right? So you're basically increasing the amplitude. By increasing the amplitude, the sound increases. So the amplitude actually determines the loudness. The loudness of the sound depends upon amplitude. Is that clear?
Yes, sir.
So say that if two sound waves have been drawn here, this one and another one have been drawn like that. So which one out of these two will have more amplitude and will have more loudness? Sound wave A or sound wave B?
B.
B. Why? Because the amplitude is more, no? And here the amplitude is less. Got it, Priyanka, Mustafa, Abu Bakr, and everyone? Okay, good. Take a look at this also here, right? A sound wave whose amplitude is less, it means it will be a kind of a quiet sound, but it will be loud sound. Okay. You guys answer these questions now. The amplitude of a sound. By the way, there's one more thing I will tell you. See, the loudness of the sound is not measured in decibel, by the way. Loudness of a sound is measured in decibel. Decibel is actually a SI unit. It's a SI unit to measure the sound. Okay. Yeah. Answer these questions. The amplitude of a sound wave determines its,
Loudness.
that is loudness. A louder sound has a dash amplitude.
Higher amplitude.
Okay, what about you guys?
Yes, higher.
Right, no? Higher amplitude. Good. What does the amplitude of a sound wave represent? Does it represent a speed, loudness, pitch, or wavelength?
Loudness.
Loudness.
Loudness, exactly. How the amplitude of a sound wave is related to its energy? It's an interesting question and simple also. Mhm. I'll be drawing two diagrams. You guys will be able to answer it obviously. Which one is having more energy? A sound whose wave looks like this, or another sound whose wave looks like this. Which one has more energy?
So the
Sound
one
wave
on the right.
A or B? On the right, no?
The-
Correct. Also, you will agree that this one is having higher amplitude, right? This one is having lower amplitude. So if the sound wave is having a higher amplitude, its energy is more, right? Its energy is more. It's having more energy. Hope that much is clear. Okay. Now let's learn about the speed of the sound also. Okay. So you all know the formula. Speed is equal to distance upon time, right? Can we also write down this formula? Speed is equal to distance multiplied by 1 upon time. We can write it like that, no? No issues, I think, right?
Yes, sir.
Yes, yes, everyone?
Yes, sir.
Good. Now, since we're talking about the sound wave here, we are talking about the sound wave. So time, we know like time is going to be the same here also, but what will be the distance for it? The distance of the sound will be measured in terms of its wavelength, right? You'll be measuring its wavelength like that, no? This added to this. So that will be its distance, yes or no? In case of the sound wave, the distance will be its wavelength now. Okay, that is the thing. So in case of sound wave, distance is equal to wavelength. So in place of distance, we will write down wavelength here. Okay, and 1 upon time period is same as frequency. Frequency is having an inverse relation with the time period now. Getting it? So in place of this, where speed is written as distance multiplied by 1 upon time, we have just learned that for a sound wave, distance is same as wavelength. So in place of distance, we will write down wavelength. And you guys remember the relation frequency equals to 1 upon t? Yes or no?
Yes, sir.
Okay. So 1 upon t is written here now, 1 upon time. So 1 upon time period, in place of that, we can write down frequency. Okay. So speed of the sound wave can be known if the wavelength and the frequency is given, right? If the wavelength and frequency is given, you can calculate the speed of that sound. I hope that should be clear.
Yes, sir.
Okay. Usually question to this might not be asked, but sometimes the examiner might ask. So I included that too. Okay. Now, generally, this is the speed of sound across different mediums, but it differs also depending upon the humidity, depending upon the temperature, etc. But generally, the speed of sound in air is 340 meter per second, in water is 1500 meter per second, and it is in solid, like in iron or in steel, it is around 5000 meter per second. Why is the speed of sound increasing here?
Sir, uh, sir, because water
Okay.
and iron as a medium are more densely packed with particles, and sound uses particles to travel, and in air, particles are actually
Exactly.
scattered on fewer quantities.
Mm. So we can say that the speed of the sound depends upon the density of the medium, right? We can say that now, right? So the speed of sound increases with the density of the medium in which they are traveling. Okay. Now say we have a sample question. We have this question here. The question says speed of sound in air is approximately, let's say, 343 meter per second. And if a sound wave travels for 10 seconds, how far will the sound travel in the air? Hmm. Use some simple logic. Using simple logic, you can calculate it. You know the formula: speed equals to distance upon time, right? And in the case of sound, we have discussed that speed is equal to wavelength multiplied by frequency, right? Wavelength here is same as distance now. Yes or no?
Yes, sir.
Okay. But here in the question, wavelength is not mentioned, so we can simply stick with this formula, right? You can simply stick with this formula. If in the question like wavelength was given, right, then we would have using this formula to figure out the distance. Okay, distance will be basically whatever wavelength you will get here, that will be same as the distance it will be traveling. Okay, but here we have to find out the how far will the sound travel in the air. So use this formula simply. Distance will be equal to speed multiplied by time, and that is
So option B.
option number D.
No, B, B.
B you're
B.
saying. Exactly, no, because 343 meter per second, sorry, 343 meter per second multiplied by 10 second here, that's going to give us the distance. Second cancel here, that is 3430 meter. Option number B. Okay, now say that a sound wave has a frequency of 200 hertz. What is its time period? You know that the relation between time period and frequency, they share an inverse relation right now. Either we can say frequency equals to 1 upon time period, or we can say time period equals to 1 upon frequency. Both of them are correct. So using this solution, you find out the time period. Yes, Priyanka, Abu Bakr, everyone, solve it quickly. Yeah, I'm listening, Priyanka. Tell me. Frequency is given here as 200. Okay. Time period will be different. Okay, no? Frequency is given as 200 hertz. You have to use this formula. Can I write it as time period equals to 1 upon 200? I'm simply swapping the place here. Time period goes here, 200 comes to its place. So now you simplify this and tell me the answer. You'll be getting the value in decimals, by the way. You have to simply divide it like that.
So I got the answer.
Yeah. And it is
0.005.
Sir, 0.005 seconds.
0.005 second you guys are getting.
Yes, sir.
Correct. 0.005. Priyanka, what you were getting is no, not 0.05, but 0.005 here. See, there is this one here. You will put one decimal here. You will bring one zero here. Okay, it's still not divisible. So you will put another zero to bring one more zero. It's still not divisible. So you will put one more zero. So now it is going to be 1025s are 205s are 1000. Okay, no? So that is 0.005, and the unit is second. Okay. Now, another question is given that if the time period of a sound wave is 0.02 second, what is the frequency of the wave? Here, time period is given. You need to find the frequency. Solve it. Again, frequency equals to 1 upon time period. So time period is 1 upon, like time period is given here, 0.02. So you basically simplify it and you'll be getting your answer. You're getting that answer. Yeah, it is correct. Very good. Very good, Abu Bakr. Others also do it. Yes, Mustafa, that is correct. Very good. Priyanka, you also hurry up.
Sir, we'll get the number, right? Not in decimal, right?
Yeah, we will get it in number. 1 upon 0.02 means that you will write it as 1 upon 2. After the decimal point, how many decimal places we see? 2, right? So we will simply bring two zeros in the numerator. So it's 100 divided by 2, that is 50 hertz. No?
Yes, sir.
Okay, frequency is 50 hertz. Okay. Now let's get to the third question, which is very interesting one. Two sound waves are being produced. Okay. Two sound waves are being produced. One has an amplitude of 3 centimeter. Like this here is equal to 3 centimeter. Okay. And the second wave is being produced, which has a bigger amplitude actually. And that is equal to how much? 6 centimeter given in the question. So first question is, which wave is louder? First or the second one?
The second
Which one
one.
is louder? Second one is louder. Good. And by how many times is it louder compared to the other? That is the
Two
interesting.
times.
2 times. No, it's not like that. Think about it. Think about it. Mhm. Mhm. See, in order to do this question, now we are going to find it out in the following manner. Whenever we have to compare the loudness of the sound, so actually the loudness is now proportional to the square of the amplitude. Loudness here, you have to understand important relation here, that loudness of the sound wave is directly proportional to the square of the amplitude. Square of the amplitude. So this is the important relation here. Okay, now. So here the given amplitudes are 3 and 6 centimeter. Okay. The second wave is having an amplitude of 6 centimeter, which is louder. So the ratio of their loudness is going to be 6 upon 3 whole square. So that is 36 upon 9, and that is equal to 4. So the second wave is 4 times louder than the first wave. It is how many times? 4 times louder than the second. Understanding everyone what I'm trying to say here?
Yes, sir.
Sir, we'll take this in ratio, so that will be up
Yeah.
6/3. Okay.
Yeah, since we have to compare it now, that's why we are going to take the ratio of the two. Okay, we are going to divide that. Okay, so that is 36 upon 9 and hence is 4. Okay. A guitar string vibrates 400 times in 1 second and a drum vibrates 200 times in 1 second. What are the frequency of guitar and drum and which one produces a higher pitched sound? It's actually very simple. You don't even have to calculate anything. Everything is already given in the question.
Sir, the guitar.
The guitar, clearly. Why so? Because it's already mentioned that it's vibrating 400 times in 1 second, which is clearly stating that frequency is 400 hertz. By the definition of frequency, what have we learned? We have learned that frequency is the total number of vibrations produced in 1 second now, isn't it? So in the case of guys guitar, it is given that frequency is 400 hertz because it's mentioned 1 second. If it was like 20 second, 30 second, then we were required to calculate it. But here it's already given 1 second. So again for the drum it is 200. Okay, now which one will have a higher pitch sound?
So the guitar.
Obviously guitar, right, Priyanka? Okay. Now a sound wave has a frequency of 50 hertz. Okay, try to understand this. See, sound wave has a frequency of 50 hertz. How many wave cycles will pass a point in 4 seconds? Past a point in 4 seconds. See, the language of the question might make you feel uncomfortable, but it's actually a simple question. Frequency is given here as 50 hertz. Okay. How many wave cycles will pass? Wave cycles here basically is referred to the vibration. You know, it means that how many vibrations will be produced in 4 seconds. Right
So
now,
200.
that is 200 exactly, because frequency, as you know, is equal to total vibrations produced upon the total time. Now, vibrations or oscillation we can also say upon total time here. So that is simply frequency is 50. Vibrations we need to find out upon 5, 4, no, yeah, 4. So 4 into 5, 50, that is 200 vibrations are produced. Got it now? Abu Bakr, you also got it now?
Yes, sir.
Good. Okay. There were a few more questions that I think we'll be doing that in the next class. And do the first question at least. A sound wave has a frequency of 250 hertz. What is its time period? Just 1 upon 250 simply. Right. So that's going to be how much?
250.
No, no. Frequency is given as 250 hertz. Frequency, is equal to 1 upon time period. So we need to calculate time period. So time period will be equal to 1 upon frequency. So we have put the value of frequency here, 250. So divide 1 by 250 and tell me the answer.
Got the answer.
Yeah, and that is
0.004.
exactly 0.004 second. Okay. Okay, so that will be it for today's class. In another class, we will do a few more numerical problems. Okay, na? And then we will get to learn about the range of the sound, like which range of the sound is uh, audible to the human ear, and what do we call the range of the sound which is inaudible to us. Like we basically have ultrasonic range and infrasonic range. What are their applications? Also, we'll be learning about that. Okay. Make sure you guys read something from NCERT. Okay.